My name is Kyuson.Lim. Today I would like to present about my topic of comparison between frequentist and Bayesian RNA ANOVA for class identification data. As many of us are known with only frequentist ANOVA, the Bayesian approach is different from conventional frequentist approach. The problem of frequentist approach has been associated with the focus on the null hypothesis testing and the misuse of p-value that has been critically contribute to the reproducibility crisis. Also, it was raised for the concern of using standard analysis such as ANOVA that relies on strict assumptions, and hence the research obtained may be misleading. So this emerging consensus that the generalization of the Bayesian approach is one of way of overcoming this issue. In the learning process of Bayesian ANOVA, we can compare the two rival models. One generally considers only the model updating term can be quantified by the Bayes factor. We also define the Bayes factor, the relative predictive performance of the rival models, that is the change in relative model plausibility that is brought by the data. However, frequentist ANOVA used F-test statistics, which is given by the fraction of MSR divided by MSE, not only with the use of p-value that is constructed based on the strict assumptions. The main difference between the frequentist and Bayesian framework lies in interpretation of direct probabilities from posterior distribution. Hence, the goal of this presentation is to provide a guide for conducting and interpreting Bayesian ANOVA. In the exploratory data analysis summary slide, there is total of 214 class data. However, there's 10 variables, 9 being continuous variable. According to the refractive index and the magnesium compositions, there are 82 values of outliers, which are omitted, and we can find that there are two types of 132 observations which could be compared. The exploratory data analysis shows that our continuous values were standardized with non-window type classes, which are composed of container, tableware, and headlamps, contains considerable number of outliers. A classification problem is inappropriate, and also we found that the regression method is rejected by the heterogeneity of the class types. For frequentist assumptions, the Apple-Wilk test shows the p-value less than 0.1 to violate the normality. Also, Bartlett test shows the p-value to be less than 0.1 to violate the homogeneity. First of all, the table 1 shows the summary statistics for 10 variables in class data. For classification type analysis by various scatter plots for 8 variables against the response variables, refractive index are considered. However, as to see roughly from 8 different scatter plots of class types, the classification type of problem is hard to discriminate two types of classes. Considering that the magnesium has a higher correlation with the class types for regression type of problems, a regression model is visually considered for two types of classes. The scatter plot shows that the modeling latent variables for two types of classes is not possible by the heterogeneity. Next, the table 2 shows the summary statistics of 5 types of classes. For outlier compositions, non-window type class contains most number of outliers, resulting in a comparison to be invalid. From the distribution plot of class types, there exists a distribution difference between refractive index of class types to examine statistical difference by applying one-way ANOVA analysis. The traditional meaning of analysis of variance involves, as the name suggests, a comparison of variance. In frequentist framework, the variance between each level of the categorical predictor is compared to the variance within the levels of categorical predictors. When the categorical predictor has no effect, the population variance between the levels equals the population variance within the levels, and the sample ratio of this variance is the distribution according to the central F distributions. Although the frequentist ANOVA is robust to two sample problems, the assumption of normality, homogeneity between variance, and the independence has met to such the user may then calculate the probability of encountering a sample ratio of variance that is at least as large as the one observed, which yields a p-value. Instead, the Bayesian ANOVA contrasts the predictive performance of the competing models. In order to make the predictions, the model parameter need be assigned for prior distributions. Hence, from the data analysis, when the Bayes factor equals to some constant, the observed data are some constant times more likely to occur under the model 2 than model 1. This is quite different from how frequentists use p-value to compute with. The transitive flexibility is shown by the use of phase vector, as this is a comparison of the two models, and hence it is more likely compare the relative measure of the evidence, that is to quantify the performance of one model relative to the other. For Bayesian ANOVA, let's first consider two-sample t-test. The conventional modeling for two-sample t-test is normal with parameter alpha and sigma. The null hypothesis corresponds to alpha equal to 0. Then we consider the effective size, delta equal to alpha over sigma, and set it equal to 0 by the null hypothesis test. Prior distribution of delta is Cauchy as a non-informative prior, simply meaning we do not have information on prior distribution of the parameter to assume with. Also, non-informative prior is placed on mu. The Bayesian ANOVA model for observation y is composed of x1 and theta1. Theta is normally distributed with the variance of g1 times sigma squared, and sigma squared is placed for the Jeffreys prior, whereas the g1 is placed for the independent scaled inverse chi-squared. Bayesian factors are computed by the integrating of the likelihood with respect to the power of the parameters. The integration of the parameter is performed through Monte Carlo sampling. The result of the frequented ANOVA shows that the p-value is smaller than 0.05. That shows that there exists a significant difference between class types. Bayesian ANOVA uses the BF function. This uses the uniform prior, and it shows that there exists a posterior probability of 0.99 and statistical difference. Bayesian model averaging uses the ANOVA BF. This examines the term inclusion phase factor. A model with the term is on average 0.1427 times less supported than the model without the term. The Bayesian two-sample t-test agree with the ANOVA BF that there exists a strong evidence 1110 times for the alternative model over the null hypothesis. According to our research, there is a limitation for the performance with the number of samples. From the frequentist approach, we can see that it is robust to the violation of the assumptions, but it changes by the sample size. The Bayesian approach, the ANOVA is restricted to classification difference. The interpretability shows that the frequentist approach overstates the evidence against the null hypothesis, and the Bayesian approach simply describes the posterior distribution of the effect. However, in the reproducibility issue, the frequentist has a rejection that are not suitable for underpowered experiment, and also there is a stability issue, which is the frequency returns a point estimate, and also Bayesian has no assumptions, which returns the posterior of the effect that is comparable with the observed data.